Welcome to TPM SOLIDWORKS webinar. Today's topic will cover some basic SOLIDWORKS and SOLIDWORKS simulation material related to our title, how a championship robotics team took home multiple awards this season with SOLIDWORKS. My name is Robbie Hoyler, and I am an application engineer here at TPM Charlotte. In my time after work hours, I help run a non-profit company where we teach high school students how to design and build 150-pound FIRST robotics competition robots in 45 days from scratch. We currently have 3 robotics teams under our wing that compete every year under the Queen City Robotics Alliance here in Charlotte, North Carolina. This started in 2010 with my own team, YETI Robotics, or Team 3506, which is a team of about 30 or 40 high school students today. Now I'm going to play this video to show you the reason I picked this program for our topic today is because this is very important to everyone involved, whether or not people realize it. These students are your future captains of industry. The students engage in this program because it teaches them real-life skills that they will use as a practicing professional engineer, and it teaches them those skills at a very young age. It helps the students get engaged in STEM, which is a shrinking set of skills in the United States, and it provides millions of scholarships to them. This program introduces prototyping, fabrication, machine design, machining, marketing, business planning, leadership, and countless others, including what you all are here to see, CAD. Now, before we dive into the software, I want to show you what this machine has to endure. This competition is not BattleBots, but it is not to be reckoned with. These first competitions are tough and arguably the most competitive in the world because the competition teams number in the thousands. You have to go through district events, regional championships, and then at the end, there's a world championship. There are only 4 winners at the end of the season. The game changes every year, but for this webinar, we were going to just look at 2016. First Stronghold is the name of this game. To get an idea of what the game is like, I want to take a look at one together. This is near the peak of the season. This is at the North Carolina State Championships. This was also held in Charlotte. Now, if you win the state championships, you get to go to the World Championships. The robot has had to endure 3 previous competitions, and SOLIDWORKS was absolutely crucial up to this point for success. The robot had previously started to fall apart during the second competition. Repairs were made, but it needed to hold up for these final matches. If the robot loses now, the season is over. So I'll start the video so you can see this 2-minute match. Each match begins with 3 robots on each side, a red and a blue team. YETI is the small red robot you see here closest to the screen with the blue fur on top. The premise of the game is that it is a castle attack scenario where you damage the enemy castle and capture it. The match starts with all 6 robots and they move autonomously following commands that kids program the robots to perform. This is the first 15 seconds. They cross these lines of obstacles on the field called defenses for points. After 15 seconds elapse, the kids begin driving the robot. Each time they cross, they carry 1 boulder, which is a foam ball, over the defenses and put it into the tower. Points are gained from boulders going into the tower, and points are gained for damaging the defenses by driving over them. There are usually 2 offensive robots and 1 defensive robot on each alliance that contribute to victory. 1 robot on red would fire high on the tower for bulk score, 1 would go shut down the other alliance scores, and 1 robot would use speed runs to destroy the tower as fast as possible for red. And that was YETI's job, that you see them crossing the middle now. Like a mechanical game of chess, the plays the students come up with for these 2-minute matches are often fiercely competitive and very well thought out. The draft picks that these teams fight and qualify for often reveal certain strategies being played like you see here. The defenses are made out of steel, and they do not give way if you do not align properly when you cross, causing potential damage. Luckily, the game design committee provides a full CAD file of the field, so students can design around the obstacles. The other robots are often in your way, causing you to miss shots and to push you around a bit to prevent scoring. This is a very rough game on the machine, so design must be carefully considered beforehand. The largest challenge is fitting all the devices the game requires inside of a 14-inch height, which was the height of the lowest obstacle the robot had to go under at times. Now, even we underestimated how rough this particular game was going to be. As the alliances play out the game and put boulders into the tower, the lights slowly decrease on the tower. When the lights all go out on the tower and the tower is weakened, and the entire 3 robot alliance must be back at the tower to capture it. If 1 robot is off the base, winning is nearly impossible if other teams try to capture. At the end here, you see the last 15 seconds of the match. Red has fully weakened the tower and all the lights are off. YETI's in the center with an alliance partner on each side. You see that scissor lift deploy out of the back of the robot and it extends to the 6-foot height. A latch is achieved and the robot lifts off of the floor. The robot climbs until a mechanical brake is activated and it prevents the robot from crashing to the floor when the power is shut off to all machines at the match end. Final matches are the best out of 3, so YETI goes on to win this one 2-0 and moves on to the World Championships. Now, as exciting as this event is, what does it have to do with SOLIDWORKS? Throughout our team history, which began with our first 9-foot tall behemoth robot in 2011, all the way up to our 14-inch tall robot that can climb 6-foot walls in 2016, the kids have entirely designed and built these machines in SOLIDWORKS. The game changes yearly, and we have no idea what's going to come next. The robot could require the capability to fire frisbees, lift other robots, shoot basketballs, stack objects, anything really. Every year we are confident and ready with SOLIDWORKS, and it's the kids, not the adults, who design all of these machines using the SOLIDWORKS product family. What I want to show is that if these kids in high school can use this software to create this machine and all these other machines, then practicing engineers can use this software and these tips as well. Today, here are the 3 main points I want to show you using the robot data set. I want to show you how we won so many awards this season. Fast turnaround in manufacturing played a major part in our season. Load testing with SOLIDWORKS simulation, and experimental design, increasing your design speed and changing your workflow so that you get faster. Time is of the essence for us, and time is money for engineers. So let's talk about our first topic, fast manufacturing turnaround. The first weekend in January, the kids learn what the game is. From there, we have 45 days to bag a completed robot from scratch, and we cannot touch it again until competition. With SOLIDWORKS, we create a perfect copy of our robot so that we can still keep designing changes even after we have no access to the mechanical robot itself. This is crucial to us because we can bring 30 pounds of parts into the competition with us each time, which means we do not need access to our assembly in between competitions to design something to fit on the bot. We make modular assembly a priority so we can add and remove subassemblies with ease for repairs and design changes. Let me show you with a case study. This belly pan on the robot was initially created out of expanded mesh plate, which we've historically used every year. You can see this on the picture on the left here. This little triangular shaped pieces here, these little diamond shape, that is the expanded mesh that we typically use. For this competition, it simply did not work. The mesh had to be cut around the drive system and other important features such as the motor access cutaway you see in this first photo here. This weakened the belly pan, and during practice we started to see the pan sag. We added many changes to it to get us through the first competition with a win. But this pan effectively lost us the most important match of our second competition, and we ended up losing because when we went over one of the tallest defenses, it rattled the gray electrical board that you see in the photo, and the robot died on the field for 45 seconds. That gray board, the NI Robo Rio, is basically what controls all operations on the robot. So 45 seconds, that's effectively half the match, and not something you really want happening on the last set of the semifinals. Since we only have 6 hours in between competitions to unbag the robot, make changes, and put the robot back into the bag, SOLIDWORKS really saved the day here. So let's take a look at the data. This is the belly pan, and this is truly the heart of the robot. Replacing it is the most frowned upon design change you can make besides changing the drive system. Everything is connected to this pan that makes the robot run. With the complexity of the geometry and needing it to fit perfectly to square the frame, we were able to create this part using our existing assembly and perfectly create each notch so that we had access to the motors, the roller chain for easy maintenance, and other electrical components. Without SOLIDWORKS, this part would never have been created and installed in time. Our sponsor cut this 3/16 plate out on a water jet. We were able to make sure that it aligned with every single rivet hole in the frame assembly. So really quick, I'll show you where this goes on our robot. Here is the robot assembly. And as you can see, The plate here on the bottom is squaring the frame. So this frame you see here along the outside is really the main structure of the robot. Now, you don't see it in this particular drawing, but we actually did end up cutting this in half for even easier access to one half of the robot at the time, so we didn't have to take the whole pan out. So we did actually split it eventually right across the middle. But you could see all the cutouts for a lot of the drive-based components. You could see it for the motor components here that are dropping down below that, clearances for the gears. This plate had to be really strong. The front bar on this robot is made out of a 2x1 aluminum tubing. I think it's about 1/8 inch wall. And because other robots and the defenses were sometimes sideways and we were running into stuff, we actually bent this bar often enough with the other mesh. But once we actually installed this, it added a considerable amount of rigidity. Now, one of the things we actually ended up doing with this piece was we actually edited the part in the context of the assembly, drew it out, and then extruded it. And then from there, we actually created the patterns to decrease weight. Weight is always a concern. We have a very thick rule book, and weight and cost per component is part of that. So this is what we did for the belly pan. Go back to the presentation. So the belly pan is not a simple part. This is something that had to go on. It was very crucial. And if we weren't able to make this change, then it probably would have caused us to fail. We would not have done as well at state championships. Now, with only 6 hours, we could not spend any time mechanically on the robot besides removing the old plate and fastening this plate to the bottom with rivet guns. We actually replaced the electronics in 4 hours, and we had time to check all the wiring and run tests before the robot got bagged. With SOLIDWORKS, we were actually able to flip this design around from something that was not working to something that carried us through 3 more competitions durably. Another case study we can look at is the climbing mechanism. Now, SOLIDWORKS is able to generate STL files quickly for our 3D printers and let us make multiple design changes back to back if anything fails. We use simulation for this, which we're going to talk about in the next section, but the original design had 2 telescoping rods with 3D printed hooks that would fly out and latch onto the bar, and then a single motor would lift us off the ground. Now, this actually worked, but it would often trash one of the arms during the climb. We had to weigh our options literally because the maximum weight of the robot fully loaded is only 154 pounds. 3D printing allows us to make much lighter parts than aluminum and helps in design as well because parts can be made easily to fit in odd places. We did not like replacing the arms each match, so we went back to prototyping. With SOLIDWORKS, we came up with another solution that would actually fit in the back of the robot. The scissor lift idea was born out of necessity. It was our last option that would fit in our robot around the other components and still only operate with a single motor. Most kids thought this idea would fail, and I have to admit, even I doubted it would actually fit in the robot design to begin with. Remember, we could only be about 14 inches tall so that we could go under one of the obstacles. But here it is, fully stowed inside of the robot. This design missed other components by fractions of an inch when fully stowed. Since this assembly moves around a good deal as it extends, we had to use the field model and the CAD model associated with that to check the number of stages we could bolt together and compare it to the height and angle we needed to reach the latch on top of this black bar you see in the photograph on the left. The batter on the bottom of the tower is angled, which further complicates the problem. We learned that we had to tilt the lift 12 degrees to reach the bar, and SOLIDWORKS was there to tell us this before we tried to bolt it onto the robot. We actually had to machine these shims on the bottom of this lift to angle the lift back 12 degrees. If we had not done this in SOLIDWORKS, we easily would have failed because when we would have put that inside of the robot, it would have been leaning 12 degrees in the opposite direction, meaning it was 24 degrees off. With all of the assembly tools inside of SOLIDWORKS, we were able to check each subassembly design in relation to others to make sure nothing hits on the robot. Big one. Big problem. If you are designing a bunch of these moving components and you don't account for this, The robot is not going to work very well. I wish more teams actually did this. Now, with this new design, we actually had to lose some weight. So we ended up testing some 3D printed parts on our robot and found that the 3D printed motor mounts worked very well. We even lifted our entire 150-pound robot off of the ground multiple times. Now, with a 3D printed winch spool and a motor mount, it wasn't as robust as aluminum, and it was eventually replaced due to fatigue problems, but it proved a real proof of concept 3D printed parts can be used on many of these motor mounts in non-load critical locations where fatigue is not an issue. Now, the white part in this photo still works even after a lot of aggressive driving. This photograph on the left actually controls the pivot of our ball shooter. This part held up very well. It actually still works. We have copies of this. We have backups of every part. But in non-load critical conditions, this motor mount works very well. Now, the one here on the bottom, we actually use this for the winch mount. This lifted our robot, I want to say 40 to 50 times before we started to see problems with this one. So this is how we use SOLIDWORKS for fast turnaround. Our build season is only 45 days or 6 weeks long. Fast turnaround for us is a must. We have a deadline and we have no options to extend it. We have to get things done within that, and then it's completely hands off. So with our time critical crunch, we successfully bagged and tagged our robot at the end of the build season. Now I want to show you some additional things. Next, we're going to talk about load testing. Now, we use SOLIDWORKS simulation to do quick checks on our parts for functionality. Since we did not want to waste any time making parts that were not going to work, we used SOLIDWORKS simulation a whole lot through the season to identify if there were going to be mechanical issues before we had the parts printed. Since we needed a motor mount that was made out of ABS plastic, it would easily bolt to the frame, it was lightweight, would fit into any tiny space, and correctly pivot the shooter, we decided to try this method. So here I'll play a video of the shooter pivoting up and down. Right here they are actually tuning the encoder, which tells the motor how far to rotate that shooter up and down, so they're getting ranges for different positions on the field in this video. To actually create the 3D printed part that you see on the left, we placed the motor, the black part in the center, exactly where we wanted it in SOLIDWORKS, inside of the assembly, just floating in space. And then we designed the mount around the motor assembly. Once we had the shape, we decided to test the mount. We decided it needed some extra geometry after the first simulation told us that there was not enough material preventing a pivot on the part relative to the frame. We extended the geometry out with these little ears that you see on the side, these little triangular shaped pieces, to displace the load, and then we reran the simulation on the part and checked it. We did this long before we actually built anything. So let's take a look at that simulation inside of SOLIDWORKS. Here I have the part that we actually used. So these little ears, that's what I was referring to earlier. The 1x2 piece of aluminum goes right in between here along this in the Z direction that you see. And then some 1032 bolts go through and clamp this down. So the simulation we did a static stress analysis on this part. And what we did was we took our fixtures like so. We assumed that the aluminum was far more robust than this ABS plastic. So we applied fixtures to those two faces that you see here. Those are not going to move. Now, you can actually put bolts in here and apply a preload torque and everything to that, to see the stress concentrations on the part. But we deemed that wasn't going to be necessary because we were using so many bolts. We knew that there were not going to be any issues there. The additional thing that we did, you'll notice that the motor and the sprocket are not present. The gearbox is not present inside of this model. And that's because we used the remote load or direct transfer, and we applied 80 pounds force at the end of where the drive shaft is, and we applied that to the faces on the inside of the model. This is kind of a shortcut. What you can do is represent that assembly, because I didn't want to have to model those 27 little spur planetary gears that were inside of that gearbox and mesh all of that. That's unnecessary. What we really want to know is this part going to fail or not? So we applied the remote load at the location where the chain is going to be applying the torque. We put an appropriate load based on our calculations on those faces, and then we ran the simulation. So we discovered that the stress in this part, the maximum stress is here at this corner. It's 638 psi. Our yield strength for this ABS plastic, when printed, is about 6,900 psi, which is something you can get from the material data sheet from the manufacturer. Now, we printed this on the Airwolf Axiom out of ABS plastic. So that's where we got this material from. Now, if my yield strength is 6,900 and my maximum stress is 638, then I have a factor of safety that's fairly high, about 10.8 or so on this part. Now, inside of this corner, that actually might be a stress concentration, because the part isn't actually that sharp. There is a small radius inside of that. Now, something else you might take a look at when you first see this model is, wow, that shape looks very, very deformed. Don't be alarmed. If you go to the displacement plot on this, you'll see the displacement's only about 5/1000ths of an inch. So you might be asking, well, why does it look so deformed? That is simply because simulation is giving you an exaggerated deformation shape so that you can look at the deformation and tell if the behavior is correct or not. So true scale on this, you'll see the plot doesn't look like there's much change at all. And that is true. Based on the loading that we calculated, this part does not flex, even though it's just plastic. So, taking a look at this really quick, the part does fit inside of the assembly. We modeled the gearbox and just kind of placed it from, we got the CAD from the manufacturer. We placed that gearbox in the correct orientation we wanted for the design. And in this, you don't see the chain, but there is a roller chain that connects these two sprockets together. And that is applying that torque that we were taking a look at. The factor of safety on this part is about 10.8. The flexion is about 5/1000ths of an inch. Now, something else I didn't show you, but I'll go back to the model just really quick to show you what that looks like, is a fatigue check plot. In the static design, you can actually take a look at a fatigue check plot here. And basically what this will do is it'll, you put in your type of loading, whether it's on or off or fully reversed, which is the worst case loading. So I always go with fully reversed. I go with the worst case scenario. And it will tell you, it seems that the stresses are low so that you do not need to be concerned about fatigue. However, a fatigue study can provide more insight. The students only have access to the educational version of SOLIDWORKS. That means that they only have access to static stress analysis. They do not have access to the fatigue module that you see inside of SOLIDWORKS Professional or SOLIDWORKS Simulation Professional. So we didn't have fatigue to double check. So even if you have a really high factor of safety, sometimes fatigue may actually be an issue. With this, we had a factor of safety of 10.8, so fatigue was not an issue on this part, at least not for our purposes. Now, to give you an idea, I'm going to show you this other video of them testing some more. Fatigue can really destroy a lot of these 3D printed parts if you're not very careful. So this part was over-designed because the shooter wheels that you see in this small video, those two wheels at the very, very tip of where the ball comes out, those things are vibrating that assembly pretty substantially. That whole front end shakes fairly well because the wheels do have a bit of mass to them, and the ball being ejected does shake that assembly. We could not consider that behavior because we didn't have a higher simulation package. But if you wanted to, you could do a dynamic simulation if you had SOLIDWORKS Simulation Premium. So let's take a look at another case study. Now, that part that we looked at before, that one held up. Let's talk about this one. The 3D printed winch and spool mount. Same material, highly different application. We're not just holding a motor in place here. We are lifting the entire robot. We ran a simulation for this part, and here was the result. I'm going to play this video, and before I hit play, just kind of look at your eye here, right there. This white part in the center of the robot is the actual mount, and then the spool is in the center of that U-shaped part. So this is a blown up version of that and where that part is, and here we go. This was actually the first time they tried a full climb with the robot operating on its own. So no students are helping the robot out. This is the robot just on its own, and this was actually the first successful climb with the 3D printed components. There you saw the robot shake, and a mechanical latch stopped the robot from falling. So we did a lot of testing. So whenever something works once, we don't just call it done and move on. We test it. We test it for rigidity. We don't want this to fail during competition. We don't want to fall on any other robots. We don't want it to fall on any kids. We have safety concerns. So we tested a lot of this. Now, when we got to testing a lot of this part, we realized that if you make the part thick enough, you can do just about everything with this. So before we get into the details of this, let's take a look at the actual assembly. Now, it's got to fit inside of the robot. It's got to lift the entire robot multiple times. It can't do it just once. So let's take a look at the winch assembly now. And I'll turn that over so you guys can see it. And we'll take a look at the simulation. Now, in this case, I did not try to reduce too much of the geometry out of this simulation. I modeled the frame and some potential connection points here. There are lots of holes inside of the beam, so I modeled that to give it the appropriate stiffness. And then, for all intents and purposes, the gussets and things that form or bolt these together are fairly stiff. I'm not too concerned about the aluminum breaking. Our experiences, doing robotics tell us that we can bolt two pieces of aluminum together and hang the robot's weight by that from previous games where we had to climb. What we were really concerned about was the plastic. Will the plastic actually hold up to this? If I press fit a bearing in there, if I bolt this down too much, if I put too much of a preload on that, is it going to break? If I have an aluminum drive shaft running through this, is that going to break? So I modeled the bearings inside of the ends here. We've got the actual drive shaft going through there, which is actually made out of an anodized aluminum inside of there. And then we just have the two parts, the spool and the mount itself, made out of ABS. Now, for simplicity's sake, what we did was model all of the contact sets as though they're bonded or just kind of glued together. We did have a few local component contacts to stop sliding and some of the other things that were going on. We had some gaps and things in there, just build tolerances. Simulation has the option to remove those build tolerances to pretend like they're interfering and touching. The fixture I used to weigh the model down, I fixed these four ends because I know that this chassis will flex a little, and I kind of wanted to see that. And we don't have the belly pan model because it is not going to be nearly as stiff as the beams are, although it will add some stiffness. So this is a fairly conservative simulation if you think about the flex that's going to happen there. The load that we applied on this one, we pulled on this winch spool up 160 pounds. So a little bit more than the weight of the robot. We can always back this up with a factor of safety. To get farther out, we can make the spool thicker, we can make the mount thicker. But after we ran the results, here's what we found. The maximum stress in the entire assembly was here. And that is a stress concentration resulting from the things being bolted or screwed together. In this case, they're bonded and they're pulling up like those two are welded together when they're really not. They're bolted or riveted together. The maximum stress was 4,278. But I already knew this part was going to hold up, right? What I really cared about was this. And it doesn't look like there's a whole lot of stress on the part and it looks like there might be some stress in there. Well, you cannot let these pretty colors lie to you. Let's check displacement before we check the stress on the rest of this, but overall, we could check the behavior with an animation and see that it's moving only 15 thousandths of an inch, which if you're lifting that whole robot by a piece of twine, that's not bad. 15 thousandths is not that much, but that is the flex that you should see in that assembly. I've seen robots with a lot more flex. Now, if you only care about the stress in this, now the yield strength of this material is like 26,000 psi, and we're only at 4,000 psi of stress. What you have to do is go back and look at the stress inside of just this assembly by itself, because that's the assembly you're really trying to analyze. You're trying to see if there's going to be problems in this part. If you're checking this part for failure, you should plop this down in a plot of its own. So the maximum stress in this part is about 2200 psi. Remembering that our maximum stress that's allowable for this plastic is about 6900 psi. The factor of safety on this part is about 3.1 or so. And we can actually do factor of safety plots to see that as well. You see a minimum factor of safety of 6.8 here, but that's because of that press fit there. So that's actually adding some rigidity inside of there. If you model the spool by itself, you'll see that it actually has a few stress concentrations because of the drive shaft in the center. Now, the reason we 3D printed this was because we simply did not have a $300 hex broach tool available to put a hex drive shaft through there. So we decided, well, why don't we 3D print it and see if that works and save the tooling cost for that. So that's kind of what we did, hoping that this would work. So it appears, we have a good factor of safety. A fatigue check plot is not going to yield any results on this. It does not say, there's going to be a fatigue problem. But again, let's take a look at this a little bit deeper. So the part, it had to be printed out of ABS. It had to lift the entire robot, had to fit in the space. And then we had to design a brake that would prevent rapid descent when the robot was powered down. Now, at the end, the winch design barely fits on the robot. The motor's actually sticking out very close to the end perimeter, so it barely fit inside of the robot. We did do multiple lifts with this. We probably did 40 or 50 lifts in testing, just trying out different brakes and things like that, different designs. And the factor of safety, all in all, was about 3.1. Deflection was about 0.015. Now, fatigue check for linear static analysis showed no issues. But let's talk about a few other things. The drive shaft that goes through this module extended far enough outside that there was actually a pancake cylinder and with a cam on the end of the drive shaft. The pancake cylinder would fire and it would run into the cam and it would seize the drive shaft. So we would deploy that pancake cylinder, the cam would latch, and we would power down the robot. And the whole reason we were concerned about this is because when you have the robot turned on, you're powering it with electricity. The robot is controlling the motor with a speed controller, and it has a mode called brake, where if you try to turn it without input, it's going to apply just enough current to keep the motor running and in that position. It's going to try to index the motor. But at the end of the match, they power all communications on your robot down, and the robot is on, but no power is going to anything, which means that motor can't even use the brake mode for the speed controller. So if there's no current, the force to turn that motor is a lot easier. So it was enough for the robot's weight to actually backdrive the motor. So we did have to experiment with that. We'd actually have to climb with the robot and then completely shut power off to it. And then we figured out that we needed that. Now, because that brake is on there, when that pancake cylinder hits the cam, it does apply a small shock load to the drive shaft when the cam engages. Now, we tuned that down and got it down so where it would deploy softly. But between lifting the robot and that little dynamic application there, plus the fact that we're swinging around in the air as we go up, there's a lot of loading conditions going on in there. So a factor safety of 3.1 was not enough to prevent fatigue issues. Now, another one of the reasons that, although the fatigue check plot showed no issues in the linear static environment, there were actually fatigue problems with the spool, and it could be due to the fact that when it was printed, it had a honeycomb pattern inside to reduce weight. And it could be that we just didn't analyze it deeply enough. The students only have access to linear static. They don't have access to fatigue that comes handy in SOLIDWORKS Sim Standard. So because of fatigue issues, the part was replaced with an aluminum counterpart for later competitions. When we designed the brake and everything, we did all of that out of aluminum because the cylinder was steel on the bore, and if we were running that into plastic, we couldn't reduce weight there. It would snap the plastic. So the lift was successful. We made sure that the cam and the piston fixed the problem. We made sure that the 3D printed parts, if we were going to use those for competition, that they were going to last. So this is really what I wanted to show you for load testing. So there's a lot of different scenarios going on there. In this case, we used all 3D printed parts for our load testing before we printed them. Now, the last thing I want to show you for our last discussion for the webinar is this: experimental design. I want to experiment with how you design today. If I can get these kids to build a 154-pound robot, I want to know what I can do with you, our user base, to make you faster and more efficient. If you can use 2 screens, you're in luck. This exercise is for you. I want you to open SOLIDWORKS on another screen and let it load up for a moment. Now, I want to run a quick test with some of the people on the line to see how fast you are. You can opt to do this later, and if you want to share this, follow the instructions on the screen to paste it into Microsoft Paint if you cannot do this now. So take a screenshot to do that, Control-Alt print screen, open up Microsoft Paint, Control-V to paste into Microsoft Paint, and then save it as a JPEG or something for later. And then you can even print it out and have it next to you if you don't have that second screen. What I want you to do is draw this sketch on the right and time yourself. And then I want you to figure out what your time is and compare it to this. Now, for a live demonstration, I'm only going to give you 60 seconds. I'm going to play this video, and you can see how I did it in just under 55 seconds. Now, I made this fair. This was the first time I sketched a picture, and I recorded myself doing it. You can even see a couple of mouse click fumbles in the video, so this is a fair estimate of how long this should actually take you. So, watch the video after you've already done your sketch and got your time, and then compare some of the techniques. I want to see what the differences are between how you do things and how I do things. Now, there's 1,001 ways to make the sketch. There is no right or wrong way, but there are faster ways. There's always a faster way. I can even tell you a faster way to do this sketch if we really want to get down to brass tacks on that. So that sketch is now complete. So that took about 55, 56 seconds or so. So if you were doing this live, time is up. If you did not do as well as you wanted, listen up. I have all of these tips and tricks on the next slide that I used to make this sketch happen that quickly. Now, in general, if you can do this in under 60 seconds, you are typically a great user, which means you're using your shortcuts, you're using mouse gestures, and you're using good technique as you draw. Now the sketch, again, has to be fully defined, origin in the bottom left corner, all of that. You can even share this out with your coworkers if you want to test them and see how fast they are. If you ever see a SOLIDWORKS expert or somebody who claims to be really good, this is an excellent thing to hand them. So the things I used in the video were the S key, mouse gestures, the line to arc shortcut, and the inference lines, which you see in the video. Now, let's take a look at each of these. If I open a new sketch inside of SOLIDWORKS, start a new part, start sketching. The first thing that you saw me use inside of the software when I was doing that sketch was the S key. If you just type in your S key, you'll see all of these shortcuts. S is the shortcut menu. It does multiple things for you. Number one, there are 4 S keys, one for every environment: the part, the drawing, the sketch, and the assembly environment. And these are fully customizable. So if you right click and customize, you can put any command inside of SOLIDWORKS on the S key. And you have 4 customizable S keys. I'm in the sketch environment currently, so this is the one that I see. Now, here's the other thing the S key does for you. If you click the S key and you don't know where the segment command is, I can beat you to it. Type in segment right away. And then you can find, for instance, detach segment on drag command. Where's that one at? Boom, there it is. I clicked and SOLIDWORKS will actually show me where that is. I did not do that with my mouse. So that's the other advantage that the S key provides you. It is much faster to use the S key and launch a line command from the origin over than it is to do this. Come up here, click, click, and then you start doing your line. If you keep doing this back and forth junk, it's going to take you all day. So try it. Change your workflow, switch completely to the S key. I know users that don't even have their tabs open. They don't use them because everything is here on the S key. And as long as you know what the command is called, you never have to search for a command ever again. So the S key is one of the biggest time savers. Let's take a look at something else. You saw me use my S key, and then I went to my line command, then I clicked, and then you saw this little maneuver. Now, this is called the line to arc shortcut. If you're one of those people who uses lines and circles and then the trim command, stop it. Use this. This is much faster. I can usually absolutely do this 8 times faster than the user who is sketching it with circles and trimming. This is simply much faster. To do this, all you need to do is be in the line command, and then to actually perform the technique, the trick behind it is you move your mouse out and then back in, and you rotate either counterclockwise or clockwise. If you do this on accident, right click, switch back to line, and you're back in the line command. So that's how you perform that shortcut. Let's take a look at some of the other shortcuts. You probably saw me using my equal relation in a lot of these. I'm using my flyouts so that I don't have to come all the way over to the left side of the screen to add the add relations over there on the left. You see equals bolded. I can see that on my flyout, click equals up here, and I never have to come down here to the left. Much faster. Here's another one. Watch my mouse. Did anybody see that? When you hold your right mouse button in, this little thing called mouse gestures appears. I can get into a circle command, I can get into a line command, and I can dimension those things a lot faster because I can change by simply swiping my mouse into those different commands. If you set up your mouse gestures, this is by far one of the fastest shortcuts you can use. To set up your mouse gestures, right-click in the gray area or in any menu and click Customize. And then over here on this tab is a mouse gestures area. Now, I always do this first, show only commands with mouse gestures assigned, and you can see all of them. The mouse gestures also have 4 environments: part, assembly, drawing, and sketch. Mine are slightly customized. These are the ones that I was showing you were not by default, but you can set them up that way if you wish to do so. I like to put my smart dimension on my up swipe because that's just a natural thing that I like on my mouse. And everybody's different. Ultimately, I want you to do what makes you faster. When you first start using mouse gestures, I highly recommend you do just 4, up, down, left, right, and then once you're used to it, then up it to 8. It's hard to kind of remember what those 8 commands are because there's so many of them. But use your 4 mouse gestures initially, and it will make you much faster. So you saw me using my mouse gestures on this a lot because that is just the way I do some of these. Another shortcut you'll see, my dimension is set so that if I type in a dimension, it just drops the dimension on that line. That shortcut is here. You just go to your menu, and in some of the newer versions of the software, all you have to do is go to the top right corner and type in Enable On. And then if you scroll down, you'll see Enable On-Screen Numeric Input on Entity Creation. And then these two options here will show you how to turn that on so that you can just type in a numeric input. Now, I highly recommend that you turn both of these on or off at the same time, because if I just click, it will not put a dimension in there, and that's what I want. I don't always want to have to dimension every single thing I draw. Sometimes I just want to sketch it out. And the other thing that I really do, auto rotate view, normal to sketch plane on sketch creation. That's another very, very nice shortcut. You start a new sketch on the front plane, it pulls your window, it pulls your screen, your HUD area up to that plane so that you're drawing normal to the plane, so that you don't have to hit spacebar and click normal to. So those are some of the options that I have turned on automatically. Then the last thing you saw me do was I was using the inference lines to help me guide my way back when I was sketching a lot of this. Now these inference lines, I'll show you the trick with them. If you hover over them, the ones that are in yellow when you're drawing, if you click, those will apply a relation. So for instance, right now I have a yellow horizontal, so if I click that, it will have a horizontal relation. If I had my relations turned on, you can see that. There we go. And if I want to create a line down here, vertical, but maybe I also want it to be horizontal with that other point over there on the left. Well, it's in white, which means that it is horizontal, but it will not add a sketch relation. So using your inference lines will also help you sketch this fairly quickly. So from the beginning, what I did was I simply went around using my shortcuts so that I could get this sketched out fairly quickly. Now, I want you guys to try this out as well. I find that most people just do not use all of these. They think that it might be too much work, or that they might not be able to to get used to this. But for the most part, what happens is that a lot of people just develop bad sketch habits when they start SOLIDWORKS. So if you use some of these techniques, it will make you faster, absolutely guaranteed. So using your sketch relations, make sure that you use your flyouts like so. Make sure that if you haven't already, make sure you set up a good template so that you are producing consistent work. Make sure you're using your shortcuts as much as possible throughout the workflow that you create at work, and you will definitely save some money as you go through this process. So give this stuff a try, and I think you'll find that it's very useful. So my last dimension here, that's underdefined, so I'll just drop that in there. Whoops. And there we are. Delete that one out. So there are always faster workflows to do things. You could have drawn these lines out first and then sketched backwards. There are multiple ways to do this. So give this a try, and hopefully you'll see some good things come out of this as well. The other thing you could do to help speed up just not only your workflow but your design phase as well. I really want to share the value of simulation and 3D printed parts being combined together. When we printed the hooks for that first design on the climber, the first time we knew that each hook had to effectively hold 150 pounds in case one didn't latch onto the bar, we just printed that first hook that the kids came up with, and we broke it. We tested it. We put some weights on it. Chris Ivan down in Greenville, South Carolina, actually did this because he's got the printer next to his desk. And the first set that we printed, we were only able to lift about 80 pounds or so before failure. We knew at this point that we had to increase the size of the hook, and the student actually added a rib around the outside to increase strength on that. and that actually did lift the full weight. So we iterated on our design. We used simulation to get a rough idea, and then we printed it, we broke it, we realized it wasn't going to work. From there, we knew how much weight it took to break that, so we effectively doubled the thickness, doubled the strength of what we had, and then reran it in simulation. We adjusted some things in simulation so that we could make the second hook a lot better. So after iterating on simulation a couple of times, we printed the best hook, which effectively carried the load. Did the same thing with the winch spool. The winch had a hex shaft, which we did not own the $300 half-inch hex broach tooling for, so we decided we could print it and avoid broaching it completely because it could print the shape of that hex broach. That hole through the center of that spool was hexagonal, so we decided to print it. And again, the spool worked for about 50 lifts and the material fatigued, so we had to cut the spool off of the robot and replace it. If the part had been a larger diameter, we believe fatigue would not have been an issue. But the reason we didn't stick with that, the gear ratio of the motor and the spool diameter had been previously set in the design, and at that point in the build season, it was too late to rework the gear ratio and buy a new gearbox. Now, I want you guys to give this a try. So we had these tools at our disposal. We drastically decreased our design and fabrication time by at least a week on this climber design. Luckily, the winch design stayed the same when the climber was changed from the hook design to the scissor lift design. Give this a try. If you design things from scratch and you need some quick answers as to whether or not something is plausible before deploying a build to the shop, this SOLIDWORKS simulation software will usually answer the question. It has saved us a tremendous amount of time and money that could have gone to waste making something that simply didn't work. Now, we like to say, make it in CAD, print it, and break it to test it and adjust. You might be thinking, well, I don't have access to a 3D printer. Well, 3D Systems in Rock Hill, South Carolina has a program called Quick Parts. So go to Google, type in Quick Parts 3D Systems, and boom, you're on their page. They print all sorts of things, plastic, metal, different polymers, molding type stuff, you name it. They do all of that stuff. You could also buy a cheaper one. For instance, TPM, well, we sell 3D printers. We use the Airwolf Axiom, which you see pictured on the left, which is a very modest printer. It's about $3,000. Big build volume, does ABS, has a heated chamber so it doesn't warp. You could also go to UPS and FedEx. They are actually 3D printing stuff in-house now too. They have printing services. So the Airwolf Axiom is one of the fastest ABS printers on the market, and we also sell a very interesting printer that can print carbon fiber, Kevlar, and fiberglass, and that one's called the Markforge, which is only about $8,000. You would think if it could print carbon fiber that it would be worth more. That's a very cost-effective machine for some of the working parts that it can produce. So these machines are very cost-effective for many customers and are selling for decent prices, which allow you to get a quick return on investment. So, in summary, we talked about fast turnaround and how quickly we can flip a design in SOLIDWORKS to make this robotics team more competitive. We talked about load testing with simulation. Test it before you build it. Lastly, we talked about experimental design, workflows and shortcuts that can make you, as a user, faster and make your design process faster. All three of these topics helped FRC Team 3506 YETI to be successful for the 2016 season. We took home 5 titles. That was more than any other team in the world going into championships. If these young high school students can make this, what can you make today? So, reiterating, try these things. Give it a try. Just attempt to make your workflow better, make your experience better. If you have questions, by all means, contact us. Now, here I have my email, and we here at TPM are always open to our customers. If you guys have any questions about anything in this webinar, feel free to email me or send a request to TPM Solutions, which will be linked to the bottom of this video. Again, thank you guys for listening, and we'll hope to see you next time.